I'll dive right in. Again, my name is Zander Evans. I work here, let's see, sorry, let me see if I can make this. Yeah. So my name is Zander Evans here. I work for the Forest Stewards Guild, and I'm lucky enough to be able to present today some work by Dr. Clint Wright from the U.S. Forest Service. He's actually retired up in Washington. Dr. Karen Hubenstack from Northern Arizona University, soils expert. Dr. Sarah Grove, who is now at UC Santa Cruz, who helped with some of our statistical analysis. So it's a great team effort. And actually the team is even larger. You'll see from the various logos, the work would not have been possible without Santa Clara Pueblo. They really pitched in on a lot of aspects of this, and we're a great partner. Let's see. I think I gotta, oh no. Gotta work out my controls here. Uh-oh, now my annotations are in the way. Okay, maybe the annotations are too much for me. I guess I can't do two things at once. So why do we burn slash piles? This is probably obvious to everybody on the call. We have forests that are vastly more dense than historic conditions would recommend, and they are at high risk of high severity, uncharacteristic wildfire. There are communities at risk, etc. So one of the ways to get rid of that material is burning piles, right? Fairly self-explanatory to everybody out there. But I think one thing that has struck me is the amount of piles out on the landscape and the prevalence of this management technique. It's a great way to get rid of fuels when we can't afford to bring them out of the woods. So just one little note here, in fiscal year 14, there were 17,000 acres of piles just in Region 3, so essentially Arizona and New Mexico, just on Forest Service land. So there are lots of piles being built out there. And when we looked in the, I guess it's the NIFPORS database, and tried to pull out all the pile building activity on Forest Service land, again, this is only one segment of the land that's being managed out there. There are a lot of piles happening, hundreds of thousands of acres of piles being created across the West. And I don't have the numbers for more recent years, but I'm guessing they continue to be up in at least in the neighborhood of 60,000 acres a year. So this is an important impact on the landscape. And when we got into this research, we felt like it was one that hadn't received the attention it was due. So we took a number of different approaches, and I'm going to kind of touch on a couple of different lines of investigation, and hopefully they're things that if you're interested in, you can follow up on, because some may or may not be interesting to different people. So one piece of the puzzle we were curious about is what happens when you have piled material out there, slash piles, fuel reduction piles, and then you have a wildfire come, an unplanned fire, arson, something, and burn through that area. Obviously not a very easy topic to do experimental research on. So we decided, well, the first step was just to go through and try to figure out how often that happens, what are some of the anecdotal evidence around this issue. And so basically we called everyone we could think of, put out all sorts of announcements saying, hey, have you ever seen this happen? Do you have any records about it? And try to compile those to understand, what's sort of the scope. And with the idea that this might help us form research questions or identify if it was an area that needed further research. And what we found was that it's fairly uncommon. And we only found about 20 examples in the last decade. Now, there may be twice that number, but still, given the number of fires and the number of piles, that seemed fairly low. So it's not as the sort of maybe doesn't deserve the full research attention that just standard pile burning gets. And based on what we could figure out from where these events had occurred, we definitely saw some cases where when unplanned fire goes into these stands where we have piled material, we definitely see more spotting. So that was one kind of fire behavior issue that we wanted to make folks aware of. And obviously, the reverse is true as well, that having dried material sitting in concentrated piles out in the woods is really receptive to embers from other sources. So that's, maybe common sense, but doesn't hurt to highlight because it can be a real risk. And I guess the other piece of that is once you do have that wildfire in this unburned pile stand, we certainly saw cases where the wildfire effects were worse than similar untreated stands. So that's, I think, a concern, particularly when we think of all the acres of piles being burned out there, the increasing prevalence of wildfire and the increased potential for the interaction of the two. You have receptive piles, and there is potential for that behavior to be worse. That said, we also saw cases where perhaps because, well, the reasons for this are a little bit unclear because it was an anecdotal survey with only 20 examples. But there were definitely cases where fire behavior was less bad in stands that had been treated and piled than in neighboring untreated stands. And some guesses are that the fuels have been rearranged, right? So they're in a place where maybe the effects aren't as bad. And then also we saw a couple of cases where stands that had been piled, there was some access. So firefighters had ability to get there, and they had ability to, conditions were such that they could fight the fire in those areas. So there's probably more to look at there, although, as I say, it's maybe not as common as I might have thought initially. So back to our specific study, we worked, this is a picture from Santa Clara Pueblo, where we were lucky enough to work with the tribe to implement this experiment. We built, sort of as per their standard fuel reduction policy where it was appropriate, we built piles that were about 4 feet high and about 8 feet wide in diameter. And this was just a stand. We worked with them to find a stand where they were planning to do this work anyway. And then we put some experimental parameters on it. We then paired this site, Ponderosa Pine, about 8,000 feet elevation, pretty standard for New Mexico. It's a beautiful spot, but in terms of the specifics, not uncommon. And we paired it with one that was fairly similar, all the way up in outside of Wenatchee, Washington, on the national forest up there. And so we had this sort of two different sites. And one element of these sites that, well, there are two elements I should highlight. One, obviously, Washington gets, even on the Wenatchee side, gets more moisture than we do down here in New Mexico. So that was a difference between the sites and kind of plays out as we see some of the results. The other factor was on Santa Clara Pueblo, they had removed material that for fuel wood. So tribal members had the opportunity to come up and with pickup trucks or whatever and get the fuel wood they wanted. So the sort of 100 to maybe even 1,000-hour fuels had been removed from the site, and so wasn't very prevalent, maybe one or two pieces in these piles that we built. Whereas in Washington, they were much more massive. They were just same size, but just heavier material. So we built out a bunch of different piles, 50 different piles, and we built some in the fall, some in the spring, and then burned them over a 4-year period to try to get some sense of how the age and season of building affects these piles over time. that was the sort of fundamental piece of the project. We measured all sorts of stuff from soils to soil heating. We don't have all the data, just seems to be taking forever to kind of crank through all the details of it. But I will present some stuff that's coming out in the Journal of Forest Ecology and Management soon. So finally seeing the light of day, and other material is available in the final report. So one of the things we did was we weighed all the material before it went into the pile. So we know exactly how heavy these piles were. And, you know, it was crucial to kind of tie down some aspect of these piles so that we knew that, say, difference in combustion or soil heating, what was that due to just the size of the pile or some other factor. So we weighed all the material, and then, as I say, we burned them. That was the fun part. And what did we learn? Well, one of the things that weighing the piles enabled us to do is look at decomposition rates. So this was a little bit of a sort of sidelight, but I think it's worth noting because for some managers, this could be very useful. Essentially, we weighed these piles for 4 or 5 years, and then we're able to develop essentially a decay rate constant. So if you're wondering what's happened to the piles you built 5 years ago, this research could provide you some details. For one, the piles compact over time, right? They get snow on them, they just sort of sink down. And so we saw the height of the piles declining by 15% annually for 2 years after piling. So that might be a useful number for people trying to make some planning guesses about what they got out there. And then these decay rate constants, they're different for Washington and New Mexico. New Mexico decomposed more slowly. Again, we believe that's because it's drier. And you can sort of see these curves. But, you know, it's worth noting that I think there are cases where these piles sit out in the woods for 10 years. And we would estimate that they would be headed down towards 50% of their original mass by that point. I guess I said that backwards, that New Mexico decayed more rapidly. So excuse me. And I think, you know, it's not, that may just be because of the size of the material. You know, the Washington piles had heavier, denser material. And so even though it is drier in New Mexico, they decayed faster. So one of the places that those decay rates might be useful is in estimating emissions. And for some of you in places where the air regulations are pretty tight, this can be a big deal. And so there's an online calculator. The link is there on the PowerPoint. You can go on, put in the number of piles, some information about their shape, and there's sort of background information on the website as well. And then you can estimate what kind of emissions are you going to see. And one of our thoughts is that piles get built, they sit out there, and if you've got 1,000 piles out there or a number of acres that you're going to burn across, even a relatively slow decomposition is going to affect your overall mass of material that's being burned. And so, you know, on the margin, it could make a difference about whether you're over or under some kind of emissions threshold. So, you know, it might be a fine point, but we felt like it could be a contribution to have some of that information available. Okay, so turning back to this particular experiment and the pile burning we did, one of the things we measured was flame heights. So probably a number of you who are experienced with pile burning kind of have a gut sense of, you know, what flame heights might look like, and for forest types you're used to. But we felt like it's nice to have something to be able to cite. If someone asks you, well, are you really sure that it's not going to have 50-foot flame lengths? Well, here finally is something you can refer people to, because we actually recorded that for all the piles for, you know, essentially every minute of flaming combustion. this is the data for New Mexico, and what you can see is this really rapid peak where piles lit up and got really tall very quickly, and then calmed down quite rapidly. More scientifically, you can see this is all in meters, so you'll have to do that internal conversion. But you can see that even though the Washington piles were made up of heavier material, they actually had slightly similar but slightly lower flame heights than New Mexico. And New Mexico, the piles burned less high, so the flames were shorter as they sat out longer. So that could be beneficial if you're a little bit worried about crown scorch or something. You know, maybe leaving them a little while might give you a little bit of a decline in those flame heights. Below, the second half of these sets of graphs looks at flaming duration. And Washington was kind of all over the place with longer durations overall. But in New Mexico, what we saw was essentially the flame height decreased and the flaming duration increased slightly. So it seemed in that case there was a little bit of a trade-off, and probably the dryness of the piles made that easier to see vis-a-vis Washington. So just sort of summarizing that, the flaming duration was about 45 minutes in New Mexico, about an hour and a half in Washington. Again, you know, folks probably have some sense of how long piles in their particular ecosystem burn, but sometimes it's nice to have something to point to, like, hey, I'm not crazy. These other people found something similar. Here's this kind of connection between flaming duration versus flame height, and this is where we pooled the data from New Mexico and Washington to get kind of a wider spread, and that the relationship kind of holds up. So if somebody is complaining about your flame heights, well, this could be a way to moderate that. So another thing we looked at was soil heating, and we haven't done the full analysis on this yet, so I don't have all the sort of statistical significances here, but I think that a few of these graphs will tell the story pretty well. And what you're looking at here is the temperatures beneath the pile. So we had thermometers essentially in the soil, and the red line is right at the surface. And this is right under a pile, so right in the center of the pile. The yellow line is 5 centimeters below the surface. Green line is 15 centimeters below the surface, and the blue line is 30 centimeters, about a foot down. So this is one individual pile in New Mexico. And so what you can see is that right at the surface, you're hitting really significant temperatures, right? 400 degrees Celsius. So these are hot. And yet, when we look 15 or 30 centimeters below the surface, you're not even cracking 100 degrees Celsius or 60 degrees Celsius. So yeah, they're warming up a little bit, but it may not even cause biological kill. So this was really interesting. I wouldn't have guessed that this sort of temperature profile, because I thought it would have sort of affected down below further. And again, this is one pile, but we see a sort of similar pattern, somewhat different, for other piles in New Mexico. And we can also see sort of the time along the x-axis, how long that heating was. And on here, the dotted black line is the line where 60 degrees Celsius is, which, you know, that would kill living cells. So we can see that even fairly deep at that 30 centimeters, there are a few seconds in there, a few of those blue circles that pop above that line. There's some we're sort of arguing about whether those are just sort of outliers or whether another theory is that some water or something else sort of precipitated down for a minute, causing that spike in heating. But again, basically, what you're looking at is right at the soil surface being quite hot for up to 10 hours, and then below that, fairly minimal impacts. Oops. In Washington, we saw much higher peaks. Again, heavier material, it can generate more heat, it can generate that for longer. So in this case, it stayed above, at least at the soil surface, it stayed above 60 degrees C for a whole day. So obviously anything living in that area would have been killed. But again, below the surface, we're seeing pretty minimal heating. I think that, and these are fairly small piles in an operational sense, 4 feet high, but I thought these were pretty interesting results. Another way to look at this, we looked at it both depth, which the last few graphs elucidated, as well as sort of horizontally. And so when we kind of integrate those, this is trying to get this picture, the gray area labeled slash pile. Well, that's where the pile is. And you can see those red temperatures, right? That's right at the surface, fairly high up. And those are pretty hot temperatures. And I converted this to Fahrenheit just to try to make it a little easier to understand. But then out sort of towards the edge of the pile and deep, we're only hitting 80 degrees, 50 degrees, 70 degrees. So pretty minimal, if zero impact out at those areas. So I think one of my take homes for this is, yes, slash pile is obviously heating up the soil, but the area that we're most concerned about is probably fairly limited. Particularly, again, these are for New Mexico piles, so these are the lighter piles. Washington, the range of red values is going to be a little bit bigger, but still fairly similar. A third way to kind of try to conceptualize this, you can see we're kind of working through the data analysis because we're trying different ways to visualize it. These blue circles are representing the number of seconds above 60 degrees C in the soil. So what you have to imagine is that at the 0 point in the upper left is the center of the pile at the soil surface. And then as you go down, the negative y-axis indicates you're going deeper into the soil. And as you go to the right, you go away from the center of the pile. And all the black dots are where we have thermometers. And so you get sort of this idea that, yes, right at the center of the pile, we've got 730 seconds, however many minutes that is, of above 60 degrees C. So, anything living in that area was killed. But as we go out towards the edge of the pile, right at the edge, at the soil surface, we hit 10 seconds above 60 degrees C. Whether or not that's going to kill everything there, I think it's somewhat debatable. So another way to look at it, this is one pile. Here's another example, maybe a lighter pile. And so you get some sense of how these vary. So that data will be coming out soon, but if you want the kind of first cut at it, the final report is online and I can share that. And I see some questions here about soil temps and soil moisture, so I can talk about that a little bit later. So consumption, we do have some good data on that, and pretty good fuel consumption, 95% in Washington, about 90% in New Mexico, and fuel consumption was unaffected by fuel moistures within the range we measured or by compaction levels. So I thought maybe as these compact over time that we might see a change in fuel consumption, but we didn't really see that. So I want to tie in some other research here that found fairly similar results. So this is some work I pitched in on in Arizona. And this work looked at both the kind of same hand-built piles of similar size, and they found 92 to 94% consumption in those piles. So sort of lining up with what we found. They did find, in that case, we looked at some bigger piles, some machine-built piles that had much higher consumption, sort of 99%, partly because they start out so large. So if you're looking at the remaining fraction, it's really tiny. And also, they burn really hot. So there is also some research on the consumption and remaining charcoal from a range of pile sizes out there. So I'm happy to share that publication with folks who are curious, but provide some larger context for this work. So here's the data we have on consumption, and I see Marissa's asking about consumption measured by weight. Yes, it's because we had the dry weight of the piles, and then we essentially took material out of the piles, dried it, and measured that consumption based on those two masses. So in Washington, fuel consumption didn't really change over time. In New Mexico, we saw a slight decrease over time in consumption. It's not exactly obvious to me what was sort of driving that, but it may just have been the age of the piles and as they decomposed over time that we saw that reduction in consumption. And another element that we were really interested in was consumption in charcoal. So one of the things, obviously, you burn stuff, you produce charcoal, and piles, given the number out of the landscape, we're thinking, hey, this could be a contribution to sort of our understanding of the carbon picture in forests. So essentially, the charcoal fraction fuel consumption is a trade-off. As you get greater fuel consumption, you're going to be producing less charcoal. Fairly obvious, but there is also a wood fraction, sort of unburned material, that could confound this. And so it's nice to sort of say, oh yes, your basic common sense understanding does hold out there, and we have some data to back that up. So when we look at charcoal percentage of the pre-burn pile weight, and that's dry weight, New Mexico generated about 3% charcoal, Washington a little over 1%. Washington piles were heavier, so the absolute amount wasn't quite as different between the two piles or two sites. The percentage of charcoal was unaffected by fuel moisture, compaction levels, pile age, or burn season. It didn't, at least within the ranges that we had in the replication, it didn't have a significant connection there. And you can see that the New Mexico piles are on the right. There's a poorly labeled, sorry. And the Washington piles are on the left. Washington a little bit more consistent. We had a little bit more variation across the New Mexico piles. But the other sort of way we were thinking about this is, okay, well, so that's on for an individual pile. We can think about, okay, 90% of it is being consumed. And again, this is sort of the New Mexico numbers. Creating 3% of this charcoal. There's some leftover wood. And I should note that these piles were just allowed to burn unassisted, essentially. We lit them and then they burn. And, common practice is if you're standing around nursing these things, you might chunk stuff in, throw stuff that off to the side, get it back in to make sure you get greater consumption. So I would say this is the unattended pile consumption. And so that 7% of wood is stuff that kind of was off to the sides that just didn't get consumed. So each pile here is generating, 4 pounds of charcoal. And then as we start to sort of scale up, okay, well, now we can actually think about across an acre of pile burning. Then it depends a little bit on the density of your piles. And so the paper or the final report talks a little bit about how many piles we had out on per acre. But just in this sort of experimental case, we're talking about 70 pounds of charcoal across an acre in Washington and 150 pounds per acre in New Mexico. So not huge numbers in sort of global carbon sequestration numbers or something, but also not nothing. And going back to this Arizona study, one of the points that Dr. Finkel made in this paper was that the amount of charcoal sort of left on site which is pretty good storage of carbon, actually was about the same as the energy, or the carbon used to drive the machines, et cetera, the fuel carbon to treat the site. So if that puts it in any kind of context, that's kind of nice to know. I think there's some, depending on where you are in the policy chain of these things, some people worry about, well, hey, how much carbon is going into fuel treatments versus what's left on site. And so knowing that, at least in this pile burning case, that the carbon lost from chainsaw fuel and truck gasoline and that sort of thing is on about the same order of magnitude as the carbon that is sequestered on site in charcoal, that's useful to know. That brings me to the end of my formal presentation, and I'll jump into some of these questions. I guess before I do, I should definitely thank, there are a lot of people involved, from folks on here on staff at the Forest Stewards Guild. The team, the forestry team at Santa Clara Pueblo was just awesome to work with. I didn't work as closely with them, but the folks up in Wenatchee were a huge help, and obviously my collaborators. So with that, let me dive into some of these questions. So let's see, Adrian is asking about baseline data, pre-pile placement, pre-pile burning, soil temperatures taken. If so, at 15 and 30 centimeters, what was the temperature increase from baseline? So yeah, let me go back. And again, I sort of have to apologize that we don't have these fully analyzed, but most days we did the burning, we started early enough in the morning. And so you can see, let me see if I can make this annotation stuff work again. You can see this end of the graph, that's the baseline. And essentially there's some elevation at 15 and 30 centimeters in this particular pile for soil heating, but not really anything that you would notice. And actually, for some of these graphs, they go on far enough so you can see the diurnal change in soil heating. And in some cases, the pile burning is less important than the diurnal heating at those, say, 30 centimeters depth. So the soils were pretty cold to start with in most cases, and we do have that data. One of our challenges now is how to summarize that aggregated over these piles. And so Landmore asked about soil types and soil moisture levels. So soil types, we do have that. Let me see if you guys will bear with me here. I'm going to try to pull that up. Sorry. You know what, man? Maybe Lan, I'll email you that. They're having trouble getting through to that section here. The soil moisture, there were definitely days, some of the burn days had higher soil moisture. As we work through the soil heating data, that's going to be definitely a component, because obviously you have to drive off that moisture in the soil. As everybody on the call probably knows, that our New Mexico soils, unfortunately, particularly between 2011 and 14, just weren't all that moist. So let me get hang on, see if I can get to our, just rattle off, that's the wrong file. Let me just find this for you, Lan. So, let's see. On the in New Mexico, they were pretty well drained, gravelly loams in the Totovani series. I don't know if that, Lan, how much of an expert you are on this stuff, if that tells you anything. Up in Washington, they were also well drained. They were a sandy loam. They were an ashy sandy loam, I guess, in the Daniel Lake series. So I can share that with you if that helps at all. I think that probably, I mean, you're smart to ask that question, Lan. I think that does make a difference. And then, yes, I guess I talked a little bit about the consumption being measured by weight. So with that, I'm open to other questions. If you want to unmute your line and just go ahead and ask a question, you're welcome to. We have a couple more minutes, or we can end early. That's fine by me too. All right, I'm not seeing any questions flying off the presses here. Yes, Marissa, let me, I'll paste that name in here because I may be saying it wrong. So the Washington soils are now pasted in there. And maybe I'll take a second and paste links to the material that's already published in case anybody is interested in that. And in the follow-up email to the webinar, I'll also, oh, great. Thank you, Marissa. That's awesome to have the full story there. Okay. So here's some links to some of these reports. Yeah, okay. So the first one there is the unplanned wildfire in areas with sash piles. There's the decomposition rates. There's Dr. Finkel's work from Arizona, and then the final report. And so a lot of the details, if it's helpful to you, a lot of the details are in there. Or of course you can email me or text me or something, and I can provide you more info. Any other comments? Anybody? I'd also be curious if anybody has stories of unplanned fire in areas with piled fuels. So Pete asked about PowerPoint. Yes, we'll have a recording of the whole endeavor here, and that will be shared up on, well, you'll get a link to it, and we archive this stuff on Frames, which is the Forest Service archive site. So yeah, you can get to it that way, Pete. Well, I appreciate everybody joining today. It's always it's great to have everybody on the line, and hopefully some good information over your sandwich or lunchtime. And please do consider joining us in 2 weeks for the drone webinar. And if you have ideas for other webinars, if there are things that, burning questions about piles that you feel like I didn't even research, let us know, because these are the kinds of, it's good to get feedback from folks working or planning out across the region to know what issues are really of most relevance. Good. Well, I think with that, I'm going to close off the webinar and have my own lunch. So thank you very much.